Welcome to today's explainer. I want you to think of chemistry not just as a bunch of boring equations on a whiteboard, but as literally the ultimate 3D construction kit. And in this kit, there's one undisputed master building block, carbon. Today, we're putting everything we know into practice with our carbon chemistry and molecular model Capstone. Okay, let's dive into this. Here's our quick roadmap for today. First, carbon's ultimate superpower. Second, decoding hydrocarbon models. Third, a pause, check, and reflect segment. Fourth, the model building challenge. And fifth, a recap and transfer. Section 1, carbon's ultimate superpower. Let's start with a bit of a mystery, all right? Right now, there are an estimated 10 million known organic compounds. So how on earth can one single element be primarily responsible for such an astronomically high number of unique molecules? Well, the answer comes down to just one number, 4. This right here is the fundamental rule of the game. Carbon's ultimate superpower is its unique ability to form exactly 4 strong bonds with other atoms, and that absolutely includes other carbon atoms. And this rule of 4 acts exactly like a set of those interlocking toy blocks you probably played with as a kid. Because carbon can connect to itself and other atoms 4 separate times, it can build an unbelievable diversity of structures. We're talking straight links of chains, branching out in all sorts of wild directions, or even looping back on itself to create these complex rings. Moving right along to Section 2, decoding hydrocarbon models. It's time to read the blueprints. Now, when you're looking at paper, you usually just see a flat, 2D condensed chemical formula, right? Take ethane, for example, C2H6. But here's the thing. These flat formulas aren't meant to show the true geometry. In reality, these molecules are actual 3D structural shapes taking up physical space in the real world. And what's really interesting here is the actual geometry of those carbon chains. You see, atoms naturally repel each other. Because of that, the bonds in a carbon chain don't just lay flat in a perfectly straight line. Instead, they push each other apart to a very specific 109.5-degree angle. And that specific angle forces those so-called straight chains to actually form a 3D zigzag shape. Which brings us to Section 3. Pause, check, and reflect. Time for a knowledge check. All right, student scientists, it's time to put on your hard hats. We're going to run through 2 rapid-fire construction checks just to make sure your foundation is rock solid. Here is your first prompt. If you have a straight chain of 3 carbon atoms, which is propane, how many hydrogen atoms are needed to finish the molecule? I want you to hit pause on this explainer right now, use that rule of 4 to calculate your answer, and hit play when you're ready. And we're back. Did you get it? The answer is exactly 8 hydrogen atoms, making the formula C3H8. If you nailed that, fantastic job. Let's quickly break down the math based on carbon needing exactly 4 bonds. The 2 carbon atoms on the ends are bonded to only 1 other carbon, so they need 3 hydrogens each. But the carbon in the middle? It's already bonded to 2 carbons, so it only needs 2 hydrogens. 3 plus 2 plus 3 gives us 8. Okay, ready for check number 2? What is the structural difference between a saturated alkane chain and an unsaturated alkene chain? Go ahead and pause the explainer again, think back to those chemical bonds we discussed, and hit play when you have your answer. Let's unpack the reasoning behind this one. Saturated alkanes contain only single carbon-to-carbon bonds. Unsaturated alkenes, on the other hand, contain 1 or more carbon-to-carbon double bonds. The really crucial point to take away from this is how that difference changes the physical shape. Single bonds are those flexible 109.5-degree zigzags we looked at. But double bonds? They're rigid. They lock things in place and prevent the carbon atoms from rotating freely, which completely transforms the 3D geometry of the entire molecule. Section 4, the model building challenge. Here is your engineering prompt. You've mastered the blueprints. Now, welcome to the climax of today's explainer. This is a strict engineering prompt where you get to apply literally everything you've just learned about our master building block. Here are the 3 strict constraints for your challenge. Step 1, build a hydrocarbon with exactly 4 carbons. Step 2, it absolutely must be an unbranched chain, meaning a straight, continuous line of carbons. And step 3, ensure every single carbon has exactly 4 bonds, filling in the rest of the empty spots with hydrogen. If you follow these rules perfectly, you'll have successfully built a molecule known as N-butane. Give it a shot. And finally, Section 5, recap and transfer. Let's wrap things up. Incredible work today, everyone. You've really shown that you understand the true mechanics behind these molecular structures. Let's quickly hit the key takeaways from today's capstone. First, carbon is the ultimate building block because it forms exactly 4 strong bonds, period. Second, when we're dealing with saturated alkanes, those single bonds create a very specific 109.5-degree 3D zigzag shape. And finally, introducing rigid double bonds in unsaturated molecules fundamentally changes that 3D shape. Before we go, I want to leave you with one final provocative thought to chew on. We know carbon can form straight chains, branches, and rings. So think about this. If a carbon chain forms a closed ring instead of a straight line, how does that actually change the number of hydrogen atoms needed to give every carbon its required 4 bonds? Try visualizing the 3D geometry in your head. Maybe sketch it out on some paper and see what you discover. Keep building, keep questioning, and I'll catch you in the next explainer.